Let's now take a look at an RC circuit example. I would encourage you to pause the video and try to work this problem by yourself, or at least get it started, and then come back to the video to watch how the solution plays out. So there are a couple differences we notice right away in this circuit. We notice that now we have specific values for our components. So we have 15 volts, we have ohms for our resistances, we have a 3 microfarad capacitor. The other difference is that we have multiple resistors. So we'll see how those things play out in a little bit. But in this problem, we're told we have a switch that has been open for a very long period of time prior to t equals 0, and it closes at t equals 0. And what we want to do is we want to find an expression for Vc of t, our capacitor voltage, for time t greater than 0. And so one thing that is important to notice or comment on briefly is, what does this mean when we say that the switch has been open for a very long time prior to t equals 0? So essentially we're saying that our resistor and our capacitor over here have been disconnected from any type of voltage or current source for a very long time. We could calculate the specific time constant with this 50 ohms and this 3 microfarads, but by saying a very long time, we're essentially saying that any energy that might have been stored in this capacitor has since been dissipated, such that we now have a voltage of 0 across our capacitor. And so that's going to be useful, of course, as we talk about our initial capacitor voltage. So as I've mentioned in several of the previous videos, my personal preference and what I would encourage you all to do is to become comfortable with using this general equation from the previous video to solve these types of transient RL and RC circuits. If we're going to use that general equation, there are 4 values that we need to know. We need to know T0, the time of switching. So in this case, that's pretty easy because we're given in the problem statement and it's written on the circuit that the switch closes at t equals 0. The second thing we need to know is our time constant tau. So in this case, because we have multiple resistors, we're going to go to that more general form. We're going to say tau equals Req times Ceq, and we'll see the specifics of how to deal with that in the next slide. The third item we need is our initial value of our capacitor voltage, so the Vc of T0. What we had just talked about on the previous slide is, because that switch has been open for a really long time, we know that the voltage immediately before switching at 0 minus is equal to 0. Remember, technically for the equation, we want the 0 plus value, the value right after switching. But again, we know that our capacitor voltage is continuous. So we already know that value, we already know the switching time. The fourth item we need is our V sub Cf, or our final value of our capacitor voltage. And so for that, we're going to analyze our DC steady state circuit. So of these 4 things that we need to plug into our general equation, we see that we already know 2 of them. We just need to find our time constant tau and our final value of our voltage VCF. So let's start by finding our time constant tau. So to do this, of course, like we saw on the previous slide, our tau is equal to Req Ceq. We only have one capacitor, so the Ceq, of course, is just going to be this 3 microfarad. So of course, micro is times 10 to the minus 6. But we need to find an Req with our multiple resistors. In this case, because the switch is closing, that 100 ohm resistor will be part of the circuit as we're going towards t equals infinity. So we do need to account for that. The way we're going to find Req is we're essentially saying, what is the equivalent resistance seen by this capacitor? And so really this is going to be the same process as we saw when we did Thevenin equivalent circuits. So we're going to deactivate any independent sources. So when we deactivate independent sources, we are going to replace a voltage with a short circuit. If we had a current source, we would replace that with an open circuit. And so ultimately what we get then is, we're saying here are the terminals of our capacitor. What does our capacitor see? Well, we have our 50 ohm resistor right here, and we have our switch, which is closed, our 100 ohm resistor, and then our voltage source, which we have shorted out, right? So this is our 100 ohm resistor, and this is our 50 ohm resistor. And so again, from the perspective of the capacitor, looking in from the right, we could see that these two resistors are in parallel. And so we know that because they share the same node pair. So if we do that parallel combination, we end up with 33.3 ohms for our REQ. We multiply that by our CEQ, which again is just C, and we get our time constant. So if we keep everything in ohms and farads, we'll get seconds. So 1 times 10 to the minus 4 seconds, or 0.1 milliseconds. So again, we can kind of get a sense for the speed of the response of the circuit based on the time constant. So remember, after 5 time constants, we can say the signal is essentially at its steady state value. In this case, because it's charging up, the final value won't be 0, but it's essentially reached its final charge value after 5 time constants, so in this case 0.5 milliseconds, so relatively quick. So the other value that we need to figure out to plug into our general equation was our final capacitor voltage value. And for that, we're going to consider our DC steady state circuit. So now we're looking at time much greater than 0. So we could say, all right, well, our time constant was 0.1 milliseconds, so we could say this is our circuit after 1 millisecond or after 20 milliseconds, but really we could just say this is much greater than 0. So this could be, 1 year later. So really just any large amount of time. And so what we're looking for is our voltage across the capacitor. Now remember, we know that if we're in DC steady state from our capacitor IV equation, so let me write that here just so we can see that clearly. So our capacitor IV equation says I equals C dV dt. So in DC steady state, we are getting 0 change in our voltage, which means we are going to have 0 current, which means, again, our capacitor behaves like an open circuit as it's drawn here. So this reduces to a simple resistive circuit, and we can use the techniques we learned previously. The most simple one that jumps out of me is to use voltage division. Because we have a voltage source in series with resistors, there's no reason you couldn't first solve for the current and then multiply that by the resistance. It's just one extra step. So using voltage division, we have 50 divided by 100 plus 50, right? So our resistor of interest divided by the sum of all the resistances in series. That ratio is multiplied by the input voltage, in this case 15 volts, and we see that our final capacitor voltage is 5 volts. So now we have all 4 of our quantities. So now we just need to plug into this general equation. So this is the exact same general equation from the previous video. So we found our final capacitor voltage was 5, so we plug that into the 2 places that appears in the equation. Our initial capacitor voltage was 0, so we plug that in there. Our T0, our switching time was 0, so that just goes away essentially. And then our tau was 0.1 millisecond, so I'm going to plug it in seconds. And so it's important, if we're going to be putting time in seconds here, we want this to be in seconds as well, so that the dimensions cancel out and we get a dimensionless argument for our exponent. So we can clean this up a little bit. So of course this would be 5 minus 5 times this exponential. And typically what we'll do as well, instead of having this 10 to the minus 4th in the denominator, we'll flip that up to the numerator, so it ends up being minus 10,000 T volts. And again, this is valid for T greater than or equal to 0. The reason we can include this equal then portion is, again, because our capacitor voltage is continuous. It's also important to be able to sort of analyze the general behavior of this capacitor, or really the circuit response, from looking at this equation. So we can see that our initial value, again, is going to be 0, so we can kind of do a double check. We can say for t equals 0, this argument e to the 0 is 1, so we get 5 minus 5 is 0. As our t goes to infinity, this exponential term is getting larger and, it's getting smaller and smaller, so our exponential is going to 0, and so we get 5 minus 0. So again, ultimately our final value is 5. So always a good idea to sort of double check your equation and make sure that it is aligning with what you expect in terms of final value and initial value for your capacitor voltage.